Module 1, Functions. A relation is a relationship between sets of values. The first set of values is called domain, which is also known as the input. Second set of values is known as the range or the output. A function is a relation such that every element in the domain is paired to exactly one element in the range. And for our last term we have a piecewise of function. A piecewise function is a function made from different functions over different intervals. We know that a relation and a function can be represented through sets, table of values, diagrams, and graphs. Hence, in mathematics function can be represented in different ways. These are the representation of functions and relations. The representation using sets. The representation using table of values. The representation using diagrams. Last, the representation of functions and relations using graphs. It is also good to know that real-life situations can also be represented as functions. For a relation to become a function, the value of domain corresponds to exactly any value of range. Let us try this situation. Through the realization in the COVID-19 pandemic experiences, Kevin and Lena, both senior high school students, start saving for a charity cost. Kevin sells paintings he made while Lena sells face masks. Kevin has an initial savings of 30 pesos and saves 15 pesos every day, while Lena, who initially saves 40 pesos, saves 10 pesos every day. Let us represent the amount of money each has saved after X number of days using a function. Let us start in Kevin's savings. For the amount he saves, since he has an initial savings of 30 pesos, then we will just have to add the amount of money he consistently saves every day to that, so we will have K of X equals 30 plus the amount of money he consistently saves in X number of days, which is 15 times X. Hence, using a function, Kevin's savings can be represented by K of X equals 30 plus 15x. Let us now have the function that will represent Lena's savings. She initially saves 40 pesos, so that will be added by the savings she makes in X number of days. And that is 10, the amount she saves a day, times X, the number of days she saves. Now Lena's savings and function can be represented by L of X equals 40 plus 10 times X. What Kevin and Lena did is a good initiative to help others, but we also have to know that there are a lot of things on how we can help, especially in this time of the pandemic. When dealing with functions, we also have to take note that a function can be illustrated as a machine where there is an input which undergoes a process and produces an output. Suppose we have coffee granules as our input and it had been processed through the coffee maker. Hence we will have a hot coffee as our output. Module 2, Evaluating Functions. Similarly, we do that when we evaluate functions. Let us go back to our previous situation. Suppose we want to know Kevin's savings after 10 days. We simply take 10 as the value of our X or our input, and we will use that in our process, or in place of X in our function, so we will have K of 10 equals 30 plus 15 times 10. In order of operations, we take 15 times 10 first, and that is 150. Then we will add 30 and 150, which is equal to 180. Now 180 is our output, and we say that after 10 days, Kevin will save 180 pesos. We just did evaluation of functions. Keep being motivated, and let's proceed to our next task. Suppose we want to know the amount of money they saved in X number of days. What operation do you think? If your answer is a dish, then you are right. We have to add the amount of money Kevin saved with Lena's savings, and that will be our first operation and functions. But how do we do that? Going back to our situation, since the amount of money Kevin and Lena saved in X number of days are in functions, then need to add functions. That is the first operation and functions that we will discuss. Module 3, Operations of Functions. Since we are adding the amount of money to saved, it will be denoted by K of, which is Kevin's savings, and L of X, which Lena's savings, or K plus L of X, and this is equal to the quantity 30. plus 15x plus the quantity 40 plus 10x. Like how we add apples and oranges when adding functions, we only add similar terms or those of similar categories. Hence in this case we can combine 30 and 40, while 15x can only be added to 10x. By associative property of equality, we may have k of x plus L of x equals the quantity 30 plus 40 plus the quantity 15x plus 10x. Adding 30 and 40, we have 70. Also 15x plus 10x is 25x. So we say that the amount of money saved by both Kevin and Lena in x number of days is given by k of x plus L of x equals 70 plus 25x. And we just have added functions. Let us have the second operation, which is subtraction. For the next operations, let us use the following functions. Suppose we will be subtracting f of x from g of x. We will have the notation g of x minus f of x, or g minus f of x. In this case it is equal to 3x minus the quantity to x minus 1. We also have to be reminded that when we are subtracting functions we add the negative of the subtrahend. Since to x plus 1 is inside the parentheses, we have to take the negative of each term inside this parentheses. Taking the negative of to x is negative to x, while the negative of negative 1 is positive 1. Now we have g of x minus f of x equals 3x minus to x plus 1. We may now combine similar terms, in this case 3x and negative to x. 3x minus to x is 1x, or simply x. Hence, we say that g of x minus f of x is equal to x plus 1. We just have finished the second operation. Are you still motivated? Very well. Let us now have the third operation, which is multiplication. We are still using the same functions. Let us get the product of h of x and f of x. In notation, that will be h of x times f of x, or h times f of x. We use a dot to avoid confusion, because we commonly use x as a variable, since there are two terms in the second factor. We distribute 18x squared, we multiply it to the first term to x, which will yield 36x cubed. We also multiply 18x squared to negative 1. This will give us negative 18x squared. In just that we were able to multiply functions, hence we say that the product of h of x and f of x is 36x cubed minus 18x squared. For our fourth operation is division. We will have h of x divided by g of x. This is denoted by h of x divided by g of x, or h divided by g of x, and this is equal to 18x squared divided by 3x. We divide 18 by 3, that gives us 6, and x squared by x, which is x. Hence, we say that h of x divided by g of x is 6x. The fifth and last operation and functions is composition. In here we take the value of a functions to be an input in another function. Suppose we take the composite function denoted by f composed with g of x or f of g of x. In this case, we will be using g of x as our input, or in place of x and f of x. Hence, for every x and f of x, we will use 3x instead. We will have f of g of x is equal to 2 times 3x minus 1. 2 times 3x is 6x. Hence, f of g of x is 6x minus 1. Module 4. Solving real-life problems involving functions. Suppose the amount of face mask that Lena sells cost 5 pesos each for a purchase of less than 10 pieces, and for pesos for 10 pieces and above. Again, we have to task. First is to represent the amount one has to pay in buying a number of face masks. Since there are two conditions, we know that we will have a piecewise function. Let's try filling the missing terms to complete the piecewise function. The representation should be a of n equals 5n if n is less than 10, or 4 north if n is greater than or equal to 10. Let us proceed to second task. Try to determine the amount 20 face mask cost. Here we will evaluate the piecewise function. We take n equals 20 as our input. We take for n for a process since 20 is greater than 10. Hence we will have a of 20 equals 4 times 20, and 4 times 20 is 80. 20 face mask cost 80 pesos, which is our output. Module 5. Rational functions. Equations and inequalities. When we speak of rational in math, we deal with ratio, which is a comparison between two values. It can also be written in the form of a fraction, and that will be the focus of our topic. Rational equations are equations that contain irrational expressions. A rational inequality is an inequality containing rational expressions. Our given contains a greater than symbol, which is an inequality symbol. It also contains rational expressions which are negative to over 1 minus x is greater than 1 over to x. For our next one, the expression x over 3x plus 1 equals y is a rational function, but what makes it a rational function? A rational function is a function of the form r of x is equal to p of x divided by q of x, where p of x and q of x are polynomials and q of x is not equal to 0. Why do you think it is important to note that the denominator should not be equal to 0? Because 0 will make the value undefined. Since x and 3x plus 1 are polynomials and are expressed as ratio, and it is equal to y. Another notation for f of x, then we say that this is a rational function. Let us try solving the rational equation and inequality. Having the equation to x over 1 minus x equals 1/4. We can have the product of 2x and 4, and this will be equal to the product of 1 minus x and 1. Where did we get this? What we have can be written as a proportion, so this can be written as 2x is to 1 minus x, which is equal to 1 is to 4, and recalling our lesson in proportion, the product of the means is equal to the product of the extremes. In here, we may have to x times for equals 1 times. The quantity 1 minus x to x times for is 8x, and 1 times 1 minus x is 1 minus x. We'll have 8x equals 1 minus x. Let us solve for x by addition property of equality. We add positive x to both sides of the equation for us to have 8x plus x equals 1. Combining like terms, 8x plus 1x or x is 9x equals 1. To get the value of x, we use the multiplication property of equality. Multiply both sides of the equation by 1/9. Hence, we will have x equals 1 over 9. Let's move to solving rational inequality. Let us now try this rational inequality. Suppose we have x plus 1 all over to minus x is less than or equal to 0. The first step is to write the inequality with the single rational expression isolated on one side of the inequality and 0 on the other side of the inequality. Since the inequality has already been written with the single expression in the left-hand side and 0 on the right-hand side, then we may proceed to the second step. The second step is to determine the meaningful numbers. We do this by setting the numerator of the rational expression equals 0 as well as its denominator. Let us start with the numerator. X plus 1 is equal to 0. To solve for x by addition property of equality, we add -1 to both sides of the equation. We combine similar terms, and this gives us x equals -1. That's our first meaningful number. Let's now have the denominator equal to 0. Then solve for x by addition property of equality. We may add x to both sides of the equation. Simplifying, we will have to equals x. Hence, +2 is also a meaningful number. The next step is to divide the number line into intervals using the meaningful numbers. In this case, we will be using -1 and 2. We now have the following intervals: a, b, and c. Now we will have the fourth step. We then test values using the inequality. We start with the first meaningful number, -1. We will have -1 plus 1 all over to minus -1 is less than or equal to 0. -1 plus 1 is 0. To minus -1 is +3. 0 over 3 is 0, and it is equal to 0. Hence, we say that -1 is a solution in A. Solution in the given inequality. Let us now have the second meaningful number, which is 2. We use this in the given inequality. This gives us 2 plus 1 all over 2. Minus 2 is less than or equal to 0. 2 plus 1 is 3. While to minus 2 is 0, 3 over 0 is undefined. Hence, x equals 2 is not a solution for the inequality. The next step is to test values within the intervals. Let us take a value in the first interval, a. Let us take -2 and use it in the value of x in the inequality. This is -2 plus 1 all over to minus -2 is less than or equal to 0. -2 plus 1 is -1. While to minus -2 is +4, and -1/4 is less than 0, then we say that the first interval, a, is a solution in the given inequality, that is the set of all real numbers less than -1. We then take a value in the second interval, b, Let us take 0, that is 0 plus 1 all over to minus 0 is less than or equal to 0. 0 plus 1 is 1, to minus 0 is equal to 2. Since 1/2 is not less than or equal to 0, hence the second interval b is not a set of solutions for the inequality. Now we take any value in C. To test in the inequality, let us have 3. We use it in the given inequality, that is 3 plus all over to minus 3 is less than or equal to 0. 3 plus 1 is 4, and to minus 3 is -1. For divided by -1 is -4, since -4 is less than 0. Then C is a set of solutions for the inequality. We then combine all the solutions for the inequality. X plus 1 all over to minus x is less than or equal to 0. In the meaningful numbers, x equals -1 and x equals to only -1 is a solution in the intervals a, b, and c. Only a and c are sets of solutions. Hence, the solutions are x equals -1 interval a and interval c. Combining all this, we will have the set containing values from -infinity to -1, where -1 is included union with a set containing values between positive to and. That is solving rational inequality. Now let us try the situation. The pandemic brought a challenge in the educational system of our country. Schools have to offer distance learning modalities. Students will be kept responsible of their time for academic work at home. Hence, a student who chooses asynchronous distance learning has to budget his or her time to accomplish tasks efficiently. If a student has to spend 40 hours a week for academic tasks, and he or she has X numbers of subjects represent the time a student has to allot for one subject. Since the student has 40 hours a week for academic tasks, and it has to be divided into X number of subjects, then it can be represented as f of x equals 40 over x. We just have represented a situation using a rational function, which is also a rational equation. Let's proceed to our next task. Let's now try to represent function using a table of values. Suppose we have the following values of x, which are 5, 10, 15, and 20. Find the values of y. For x equals 5, we divide 40 by 5, and that gives us 8. For 10, 40 divided by 10 is 4. The third value, 40 divided by 15 is 2 and 2/3, and lastly, 40 divided by 20 is 2. Now let's try plotting the following points and draw a graph that will pass through these points. The first point is 5, 8, so from 0 we go 5 units to the right and 8 units going up. That's our first point. The second one we have 10, 4. That is 10 units to the right of 0, and for units above 0. The third point is 15. 2 and 2/3, so we'll jump 15 units going right. From 0 and 2 and 2/3 units above 0, and for our last point we have 20. To this is 20 units to the right of 0, and 2 units above 0. We can now connect the points to create the graph of our function f of x equals 40 over x, and there we have the graph of a rational function. Rational function can be represented by r of x equals p of x over q of x, with the restriction that q of x should not be equal to 0. So in our function, the denominator, which is x, should also not be equal to 0. Again, this will give us an undefined value. Hence we can say that at a domain, or the set of all possible values of x of the function f of x equals 40 over x, is the set of all real numbers except 0. This can be written in this set builder notation, which is one way to write the elements of the domain. Let us now move to getting the range of a rational function. We have to get the domain of its inverse, and we know that this can also be written as y is equal to 40 over x to get the inverse. Interchange x and y. This will give us x equals 40 over the inverse function. We then solve for y. Let's try it. Since this is an equation, we may use the process in solving a rational equation. X can be written as x over 1. We can start now by multiplying x and y, and 1 and 40. This will give us xy equals 1 times 40, or simply 40. We want y alone on the left-hand side of the equation. Hence, by multiplication property of equality, we may multiply both sides of the equation by 1 over x. Hence, the inverse of the function is equal to 40 over x. This can also be written as the inverse of f of x is equal to 40 over x. Again, the domain of the universe of the function is the range of the original function, Hence, the domain of the inverse is the range of the function f of x equals 40 over x. We use the same restriction that the denominator should not be equal to 0, since this will give us an undefined value, so the range of the original function is the set of all real numbers except 0, written as the set containing all y's element of the real numbers such that y is not equal to 0.